Good morning, everyone. How are y'all doing today? Good? It's a chilly day. Yeah. Thank you for coming to our final lecture in our Saturday Physics for Everyone series this fall. It's been a really great semester, and we're very excited to wrap it up with this lecture today. A couple announcements for you. So this is our final lecture of Saturday Physics. There is also Saturday Engineering for Everyone, which is in the spring. It's our sister program, but we don't run it. So there's a different group of people who does that organization. If you want to get an update about that, feel free to sign up for our email list, and I'll be sending a note to wrap up this semester and let you know about that as well. And all of our previous lectures are now currently on our YouTube page. If anyone has missed them and wants to go back and review them, they're there, or feel free to share with your friends who haven't had a chance to come in person. So, yeah, I think that's it for announcements. And let me get started by introducing our speaker today. So Dr. Jacqueline Noronha-Hostler did her undergraduate at Berea College, where she did a double major in physics and mathematics with a minor in German. She finished her PhD in theoretical physics at the Goethe University in Frankfurt, Germany in 2010. Following her PhD, she obtained a postdoctoral fellowship at the University of Sao Paulo, Brazil, followed by an associate research position at Columbia University in New York City, and a postdoctoral fellowship at the University of Houston, Texas. From 2017 to 2019, she was an assistant professor in the physics and astronomy department at Rutgers University and the 2018 Department of Energy Early Career Award. In 2019, she joined the faculty at the University of Illinois Urbana-Champaign and was promoted to associate professor in 2023. She has served on the executive committee for the Illinois Center for Advanced Studies of the Universe, the American Physical Society's Division of Nuclear Physics, the Relativistic Heavy Ion Collider, and the Alternating Gradient Synchrotron committees, and then both the MUSES, Modular Unified Solver of the Equation of State, and the SURGE collaborations. All our nuclear physics experiments. She studies high energy nuclear theory that uses the strongest force in nature to study the smallest possible scales that humanity can explore. Please join me in welcoming Professor Noronha-Hostler.
So thank you, Noreen, for the nice introduction. Hopefully you guys can all hear me okay. I'm excited to be here today. The last time I did a Saturday Physics for Everyone, it was the height of COVID. It was all on Zoom, so this is the first time I get to do this in person, which is pretty cool. So it's nice that you all came here in the freezing cold and are joining us today. So I'm going to talk to you about reverse alchemy. We're going to turn gold into the most perfect liquid that we know for all of humanity, in fact. And so how are we going to do this? So back in the day, when we think of alchemy, you wanted to take something like lead and then turn it into gold. But life has changed now. We have enough gold, and we want to do something else. We want to actually take gold and turn it into this very, very special material that existed 10 to the minus 6 seconds after the Big Bang. It's the most perfect fluid that we know in nature. And so this is what I want to talk to you about. It's called the quark-gluon plasma. We'll come back to that in a second. But before we get into this, we need to explain what is a fluid and what's a liquid. And so these are things that are slightly similar, but we need to kind of establish nomenclature here. And so if we think about a liquid, we know different phases of matter, right? You have a solid, which you can see up there with the ice here. We have a liquid, like a nice cup of water you might have just drank, or a cup of coffee. And then we have vapor, which if you took that cup of coffee outside, you'd see a lot of vapor coming up from your coffee. Now, what is a fluid? Fluid is like a liquid, but it's something that flows. And so that could actually be something that you describe as a liquid or a gas. And so you can see here, this gas, this water vapor, is actually flowing as well. And so it's how we describe the properties of some sort of material that is moving. So it's definitely not a solid, right? We're saying not a solid, but it's either a liquid or a gas. Actually, it can be something else too, but we'll get to that in a second. So let's get into some details of what fluids do. Number one, they flow, right? We already established that. It's like a river. It's moving in time. It's dynamical. It's pretty exciting. That looks really nice, right? The other thing is it cannot resist an outside shearing force. And so what I mean is if I took a water balloon and I collide it with a bowling ball, you see that it doesn't break apart or it doesn't just bounce off the bowling ball, but it has all these really cool ripples from the water balloon. And so that's what I mean, is if I punch a liquid, it's going to splash. It can't resist when I punch it. This is actually very similar to what we do in the experiments, except for it's like two water balloons that we're colliding. The other thing is that it's going to take the shape of the container that you put it in. So if I pour water into a cup, you see that it takes the shape of the container. It doesn't have any permanent shape. That's the idea. Now, whether it kind of settles to the bottom, where it's more like a liquid, or it fills to the side of the container like a gas, those are dependent on the phase of matter. But in this case, it doesn't have any set shape that you say, okay, it's exactly this shape. All right, so now if we want to talk about fluids in more detail, we need to think about different variables that are important for fluids. And so let's imagine I have a balloon, okay? And so if you've taken like Physics 101, you've probably heard about forces and masses, and we're not going to be using those variables. What we use instead is we're going to talk about densities and we're going to talk about pressure. And so what is a density? That is just the mass divided by the volume of whatever you have. So if you've got a balloon and you've got very few little particles inside of it, and all those particles have the same mass, then it's a small density, right? It's kind of empty, it's dilute. If you have a lot of little particles, and again, they all have the same mass, you're going to have a large density. So it's the difference between something like a balloon versus a bowling ball. Bowling ball obviously has a much larger density than a balloon. Now, the other thing that's really important to understand when you're talking about fluids is you need to understand pressure. And so pressure is just the force divided by the area. And so you can also think about that is if you have a lot of change of momentum. And so an example of changing momentum is all your little particles have velocities, right? They're moving around. They're not sitting still. And so you can change momentum if you're hitting the side of the balloon a lot. The more you hit the side of the balloon, the more you're pushing it outwards, the more pressure you have. And so you can see here, we have the same density here, but these guys would have more velocity. They have bigger velocity, they're pushing it outwards. And this one has a smaller pressure. All right, great. So we've kind of established the basics of a fluid, but then the question is, when can we consider something a fluid? That is not a trivial thing to understand. You might say, okay, I can look at this is definitely a fluid, it's okay, I can apply fluid dynamics, but you actually need to do some calculations. And so one thing that you can do is you define something called the Knudsen number. And so this number is telling you if a thing is a fluid or not. So if the number is very tiny, then you can say, okay, it's a good fluid. If it's bad, if it's too big, if it's like close to 1 or 2, then it's becoming pretty iffy and it's probably not a fluid. So to give you an example of what I mean, let's go to Lake Michigan up here, right? It's really, really big. And so if I look at the size of Lake Michigan, it's around 500,000 meters. And so then what I do is I take a ratio of the very tiniest scale inside the fluid. This is like an H2O molecule, so a molecule of water. And then I divide it by my large scale. That's the size of the lake. And we know H2O molecules are very, very tiny, right? And so we get a very tiny number. This is the size of an H2O molecule, around 10 to the minus 10 meters. If you divide that by 500,000 meters, you get an insanely small number. You've got 0.17 zeros going on there. It's really, really tiny. And so that means it's a fantastic fluid. A way to think about this is when you have a fluid, you're describing it on large scales. You want to see like the size of your system, how it's flowing. You don't want to see how those individuals, molecules or particles inside of it are interacting. That makes it more complicated. You need some other theory to describe that. So then the question is, well, okay, I know what's a good fluid has a very small Knudsen number. I know a bad fluid has a very large Knudsen number, but what about something in between? What if my fluid starts to get a large-ish Knudsen number? At what point does hydrodynamics or fluids break down? And so before we get into that question, we'll come back to that later on this talk, let me just tell you that we use fluid dynamics, this description of fluids, everywhere. It's so much in nature. And so you can use this in biology. You can think of how blood flows. People use fluid dynamics to describe that. You can even describe traffic jams using fluid dynamics as well. Or, and I'll get to this at the very end of the talk, you can imagine two dead stars that are rotating around each other in space and colliding, and you can describe that as a fluid dynamics picture as well. And so what is fluid dynamics? Well, it's a series of equations that tells you how this fluid moves dynamically in time. And so essentially what you're looking at is something where you have some sort of pressure or density. Remember, those are the variables we talked about at the beginning of this talk. And then we want to see how those are going to flow in time, given certain velocities and initial conditions. And so I purposely show a picture here of this because you have this nice field, and so we think of these as fields, and you're seeing changes here. So this looks really flat, and so we could say the gradients are very, very tiny. This sort of thing is essentially zero. So if we think of this as pressure, when you have these weird symbols here, that means this is zero, it's flat. What a gradient is when things are changing very rapidly. And so when you have this steep slope here, you wouldn't be wanting to like walk down that or run down that. That would make you go very, very fast, right? It's the same sort of thing. When a fluid sees these large gradients, it pushes the fluid in that direction. And so the fluid flows wherever it has very large gradients. So if this was our fluid and you had such a steep slope, you'd see a lot of fluid going in that direction. That's how we can understand this. So that's what this term here is telling you. This term is velocity divided by time is a way to think of this. It's telling you how quickly the fluid changes its velocity. And so that also depends on the local density of the fluid. And then the last thing, this weird little eta, that is viscosity. That's how sticky the fluid is. And so we'll get into that much more of what a viscosity is. But I will tell you this. If you have an absolutely perfect fluid, there's no viscosity. It's zero. If you have a little bit of viscosity, it starts making it slightly sticky. But if you have a large viscosity, it would be a very, very sticky substance, kind of like glue or something like that. All right, so let's see what happens when you have a large viscosity. I have a little video here. On the left, this has a very low viscosity. It's not very sticky. And the one on the right has a very large viscosity. And I'm going to drop two balls, and you can see them race down to the bottom. I drop them. You see the one on the left? It goes down immediately. And this one on the right, you'll see in a second, is that one's already on the bottom. There's no viscosity in that system. And look how slow this guy is going. That's because of the viscosity. They're the same size, the same tube size, everything, but because that substance has a larger viscosity, it's slowing down the flow of the little ball. All right. Good. So we've talked about viscosity. The next thing is what happens to fluids at the very extremes, at our very limit of knowledge when it comes to physics. And so one way to think about this is what happens when a fluid isn't just like moving at a normal speed. Like if I have a coffee cup here and I dumped it out, you would see a fluid flowing, but it's at a normal velocity. It's what you would expect. But what happens when a fluid moves at the speed of light? So when you're moving at the speed of light, lots of things crazy kind of happen. You can get time dilation. You have to worry about causality. Causality means that you're not traveling faster than the speed of light. The speed of light is a bound, and you cannot go faster than that. Otherwise, it's called acausal. And so this is a real big problem for fluid dynamics. If I were to take these Navier-Stokes equations, those were the equations I showed you before to describe fluid dynamics, they would break down. They would be very bad equations. In fact, what it would tell you, first of all, it would tell you that things are moving faster than the speed of light, and it would actually just, your system, if you just touch your system slightly, you'd perturb it, it would explode. And we know that's not true. We have fluids that move at the speed of light. And so there's something wrong with those equations. So first of all, like I said, they violate causality. Those equations, if we try to use Navier-Stokes and we run with a fluid that moves at the speed of light, it tells you things are moving faster than the speed of light. And we do not see this in nature. So there's something wrong. The equations have a sickness to them that we need to cure. The other issue is stability. And so the way to think about stability is I have these three different things with balls. If I have a ball that's on like a curved table and it's just sitting there, and I go flick it very, very softly, it's just going to roll off the table. It's like my equations are kind of exploding. There's something wrong with it. If I have something that's neutral, and it's on a flat surface, I flick it, it'll kind of roll. It won't go back to its original position. But if I have something that's stable, I can imagine my little ball is in a curved, like a bowl, and I flick it, and it'll move around a little bit, but then it goes back to its original position. That's what you want when you think about a fluid. If you guys shake up your coffee right now, or your water bottles, it will get, upset, it'll kind of move around a little bit, but then it settles back to normal. We know that's how fluids move, right? And so we want something that's stable, because that's how fluid dynamics works. So what do we do? Well, Israel Stewart, back in about the 70s, had a wonderful idea. Is what we need is a relaxation time before we go back to this Navier-Stokes equation. Is we need a time scale that if we perturb our system just a little bit, that it relaxes back to those equations. And in fact, this fixed the problem. It worked really well. And so the idea that we can understand this is when we're moving at the speed of light, if I have a big system like this, and I touch this side of the system, I need some amount of time for that to propagate to the other side of the system. And so that helps you to preserve causality. And so this changed the way we do the equations of motion. Okay, good. So we have some equations we can solve, but we have other problems too. Is fluids don't just move fast. They can be extremely hot. So in fact, the hottest temperatures that you can create on Earth, and we'll get to even how hot those temperatures are in a moment, but what happens is when you get to really, really hot temperatures, you melt things, right? Things that are normally together fall apart. And so if we think about like an H2O molecule, it actually melts. We don't have any molecules anymore. We don't even have atoms. We don't even have a nucleus anymore when you get to these temperatures. Everything's melted away. And so we're getting to temperatures. If I have my little thermometer here, this is where volcanoes are. This is where my sun is. This is 10 to the 12th Kelvin. It's extremely hot. So then, what happens is we have a fluid moving at the speed of light. It's really hot. And then there's one other extreme that we want to discuss. We want to discuss a very, very tiny fluid on top of everything else, if we didn't have things that were challenging enough already. And so when we have a very tiny fluid, we start to get in a little bit of a trouble with our Knudsen numbers. And so remember, when we were talking about Lake Michigan, we had a super tiny Knudsen number, 10 to the minus 17. There was a lot of zeros after that decimal point. But let's imagine now that we have a fluid that's the size of a nucleus. So do you guys know the size of a nucleus? This is essentially, if I took an atom and I removed all the electrons, this is this ball of protons and neutrons sitting at the very center of the atom. And that's around 10 to the minus 14 meters. If you want to understand like how far that is away from us, in terms of the order of magnitude, it's about the same distance to the closest star from Earth. In fact, a little bit farther. So it's really, really far away from us in terms of orders of magnitude. Not only that, but I want to even look inside of those to see what's inside a proton. Inside a proton, there's a lot of complex behavior. A proton's not just a point-like particle, but if I crack it open, there's these crazy things. These are called quarks, and the things that kind of stick those quarks together are called gluons. And so they bind together this very complex object that we often just think it's like a little point-like particle. But there's a whole world, universe inside this proton that gives it very specific properties. And that's even smaller. It's about, you take the size of a nucleus and divide by 10 to get the radius. Okay, so now my problem is that I have all three things that I need to deal with on a daily basis. I have something that's extremely small, extremely hot, and moving at the speed of light. And this comes together, the fluid dynamics that I need to use to describe this system is really tough. So the thing that is describing is this thing called the quark gluon plasma. Essentially what we do is we take two nuclei, so I've got a nucleus there and a nucleus there, I collide them at the speed of light, and out pours the quark gluon plasma. And so you can see this remnant of the one nucleus here and one nucleus here, and inside there's these colorful balls. This is the quark gluon plasma. And I'll tell you a bit more about what that is in a second. Now, the quark gluon plasma is very interesting. It's not just the most perfect fluid. That was kind of how I motivated this talk. That means it has a really small viscosity. But on top of that, it's the hottest thing on Earth that we've ever created. We have the Guinness Book of World Records for creating something insanely hot. It's also the smallest fluid that we are aware of today. It's super, super tiny. So it's the most perfect, it's the hottest, it's the smallest. It's also the strangest. There's these little particles that are called strange particles, and it's just filled with them. And it's the most vortical. So what does that mean? It has essentially little tiny tornadoes going on inside of the fluid. And so it does all these bonkers things. And we're trying to understand this property amongst all this chaos. So in order to understand the quark gluon plasma, we need to understand the strongest force of nature. And so there's a theory for this. It's called quantum chromodynamics. And I'm putting it in color because color is a key component of quantum chromodynamics, or QCD, as you often hear it be called. And so let's discuss the different forces of nature a little bit so you can understand more about quantum chromodynamics. So we are aware of 4 fundamental forces of nature. You probably all know about gravity. That's why we're sitting here. We're not floating up in the sky. So that's pretty good. You probably have heard about electromagnetism. We can use magnets. We have electricity. These are things that most people know at least some things about. There are 2 other forces that are kind of like always pushed off to the side because they're hard and they're complicated, and we don't really deal with them too much in everyday life. The first one is the weak force. It's called weak because it's a weak force. It happens on relatively short scales, like think of the size of the nucleus, and it happens very rarely. And so we can study this force in particle colliders, but we're not going to get into it too much in this talk. The other force, and this is my favorite force by far, is the strong force. It is, by its name, because physicists thought really long and hard about it, is the strong force, even though it's the strongest force in nature. And so what it does is it essentially keeps a nucleus together. It keeps these protons and neutrons in a very, very tight ball. And it's also the same force. When I showed you that like cut open proton, that's keeping the proton together as well. And so it's the force that really binds things at a very, very fundamental scale. And it's by far the strongest force. But the good news is, because if it was so strong and it was long range, it would all be like stuck together. But it only occurs on the size of a nucleus. After that, you don't need to worry about it. All right. So to give you an idea of these different scales and the units that we're going to have to use to describe them, is that we have an atom, and this is the nucleus at the very center. And here's the picture of our nucleus. It's many, many times smaller than the atom itself. And then here's the proton, and it's 1 time smaller, essentially, than the nucleus. But inside of there's these quarks and gluons that are moving around, interacting with each other, and that's also many times smaller than the size of the proton. So to deal with these things, we make our lives easier and we change our units. And so we essentially say that the speed of light is just equal to 1, because I don't want to do a bunch of conversions and I'm a bit lazy to deal with that. And then my length scales are in femtometers. So that's 10 to the minus 15 meters. Otherwise, I have to carry all these factors of 10 to the minus 15, and that gets a little complicated too. I also make my temperature super, super hot, right? I told you it was around 10 to the 12 Kelvin. That's, you can think, or sorry, that's around 11 billion Kelvin, and we use these things called mega electron volts. And then the other thing is our masses are very, very small. These are very tiny particles, and that's around 10 to the minus 30 kilograms. So we're dealing with something extremely hot, extremely small, and extremely light. Okay. So I mentioned quarks and gluons. What in the world are these things? We have a standard model that describes these properties. These have been tested for many, many years. We understand very well what these masses are at this point, how these particles interact. But what we understand from them is normally in the vacuum. That means that you have a particle that decays, and you can see those properties of the particle from that. What I deal with is not when you just have a few particles together, but you have many of these particles together, like hundreds of them, or thousands, or millions. And the properties change as you put many of them together. It's the same idea as if I have one H2O molecule, it has different properties, versus if I have a lake. It's very hard to extrapolate from one H2O molecule to know how a lake is going to move and flow over time and freeze as an ice cube and all these fun things. And so I study what happens when I put many of these fundamental particles all together. Now, the ones that I care about by far the most are these quarks here. There's up, which is the lightest one, down, which is nearly the same mass as the light quark, and strange. I also care about these guys too, but I'm not going to talk about them in this talk because they're much heavier. So they don't play a role so much for what I'm going to be discussing here. The other thing that I really like is the gluon, and I'll get to that in a second. So how do these quarks talk to each other? We can think of this, if you all might have played this game of telephone as kids, where you're trying to talk to each other with two cans. We can imagine that those are the quarks. And what the gluon is it's really the mediator that goes in between. So it's like the line between those two cans. And so it helps us communicate. It helps the two quarks talk to each other, because they don't actually talk directly. They always talk through a gluon. Now, the problem with quantum chromodynamics and the strong force is that gluons are a little bit trickier than normal. If we compare this to something like quantum electrodynamics, so electricity and magnetism, you have the photon, which is the mediator. And when it talks between two fermions, it doesn't talk to itself. So it's a pretty easy discussion. But the gluon, it likes to get and bring its friends along, and they all talk to each other too. And so it makes communication between the quarks a lot more complicated. You could have a gluon that's just sitting there doing nothing, and it decides, I'm bored, I'm going to split into two different gluons. Or, there's two friends, they're gluons, they get together and they become one gluon. They do a lot of crazy things. And because of this, that changes the theory entirely. It makes it very hard to solve mathematically. So we have to use a lot of tricks to get at QCD directly. Now, there's two super important properties of quantum chromodynamics. The first one is confinement. You might not understand what that word means, but we'll get to it in a second. The other thing is hadrons. So the name might be unfamiliar to you, but that's just a proton, a neutron. You might have heard of something called a pion or a kaon. That's just saying these are the particles in nature, and it predicts that they exist and explains their properties. And so QCD won a Nobel Prize in 2004 for work that was done in the 70s. And so we're still trying to understand many of the properties of QCD today. We can only directly solve QCD in a very, very tiny regime of all of the possibilities that we actually want to use to understand QCD. And so we have to use a lot of tricks to go beyond that. So these are the two main properties of quantum chromodynamics that you need to understand for this talk. The first one is that they're called bound states. That means that I don't have a free quark running around in nature, but it's always bound within a hadron. So I could have something like a quark, antiquark, and this creates a meson. So there's two quarks inside the meson. I can also have three quarks. This is a baryon. So these are examples here of a meson and a baryon. The baryons are probably what you're most familiar with. That's like a proton or a neutron, but there's actually hundreds and hundreds of other ones that only appear for very short periods of time. The baryons are fermions, for those who know what that means. So it means they have spin 1/2. The mesons are bosons, which is spin 1. And you can even get crazier things that we're actually just learning about today. This happened really recently in the last couple of years. We're starting to get these exotic states of matter that are not just baryons and mesons, but there's like pentaquarks, dibaryons, tetraquarks, a lot of cool things that the Large Hadron Collider is measuring. And we're just starting to learn about their properties today. So now to give you examples of common particles is we can have the proton and the neutron, that makes up the nucleus, but you can also have antimatter. That is something just like the proton, but you just change all the signs. So you have an antiproton. And the quarks, the electric charge that it carries, proton has a plus charge, antiproton has a minus charge. So you just switch you just put a negative sign in front of everything and you have antimatter. You can also get more exotic things, like a kaon, that's a strange quark. Remember I said there was this strange things going in the quark-gluon plasma? We get a lot of strange particles inside of there. And even heavier ones that have charm quarks inside too. So we have hadrons. That's important for quantum chromodynamics. But there's another super important property, and this is called confinement. And so this means that we don't have any free quarks in nature. You cannot just go measure something and find a free quark. That does not exist. And so because of this, we have to understand the properties. Why are there no free quarks? So the way to think about this is imagine I had a meson. I have a quark-antiquark pair. And I want to pull them very far apart and get one of the quarks to become free. Well, I don't know if you played with these finger traps as a kid, but you put your fingers in and you try and pull it out. And the more you pull it, the stronger the force is between your fingers. And so this is exactly like quantum chromodynamics. The more you try and pull these little quarks apart, the stronger the force between them. And in fact, the force becomes so strong that instead of getting a quark by itself, you just get magically this quark-antiquark pair that comes out of the vacuum and appears. And so you create two new mesons. And so this is the property where you would have a heavier meson that decays into its children, essentially. So you could have, in this case, it's called a rho meson, that would decay into two pions. It's a great example. We see this all the time in experiments. So what keeps it all stuck together? Well, it's the stickiest glue in nature. It's the gluons. It's because of these gluons talking to each other, the self-interaction, that it becomes just like this really sticky thing that makes it hard to pull apart the quarks. All right, so that's great. We've learned about the strong force. Why should you guys care? You know, I told you it's on the size of the nucleus. Maybe it's something that just theoretical physicists care about. We don't really need to know much. Well, the reason why you should care about this is that the mass of the universe, of the things that you can see, anything you can see, comes from QCD. Essentially, almost all the mass is from quantum chromodynamics. And so we can actually do an estimate right here. So if I take an adult panda and want to measure their weight, it's around 200 pounds. All right? So how much of that mass is coming from quantum chromodynamics directly? What we can do is the adult panda's mass is mostly made up of protons and neutrons. This is from the nucleus. The electrons are so ridiculously light, you can ignore them entirely. And so if we want to estimate how much is coming from the interactions of the quarks and the gluons, well, we can add up the masses of the quarks themselves. This is not actually from QCD. That's coming from the Higgs boson. But that's a very, very, very tiny mass. And so if we add up the masses of the quarks themselves without any gluons there, it's only 9.4 MeV. But if we want to see the entire mass, that's 938 MeV. That's many times larger than the actual mass of the quarks. And so all of that mass is coming just from either the gluons that are talking to themselves, the self-interaction, or the gluons that are mediating the interactions between the quarks. That's all quantum chromodynamics. And so the mass is huge from quantum chromodynamics. It's 99% of the mass of the proton. And so if we extrapolate this up here, and we take a very conservative estimate, we're guessing that the QCD mass is around 190 pounds and the Higgs mass is around 10 pounds. So really, everything that you're thinking about is pretty much from QCD. Now, what else can we do? Why is it interesting to study quantum chromodynamics, and what can we get from this? Well, we can start thinking about different phases of matter. We talked about solids and liquids and gases at the very beginning of this talk. Could quantum chromodynamics also have phases of matter just like water? And so if we think about water, if I add heat, I start with a solid. You guys are all used to ice living here in Illinois. And eventually spring does roll around, and those solids turn into waters. We have a lot of lakes around the city. And if you heat that up even more, you get water vapor, right? And so when you're used to looking at these different phases of matter, you add heat, and at some very specific temperature, it changes its properties from a solid into a liquid. So the question is, could I think of a temperature where I could actually melt protons and neutrons and get at quarks and gluons? And so this is what I want you all to think about. And in fact, the answer is yes. This is a lot going on. I'm not going to go into all the details here. But we can do calculations directly of quantum chromodynamics, and that can actually give me a temperature where I can melt hadrons, so protons and neutrons and pions, into quarks and gluons. It's really, really hard to get at this temperature, but we can do it here on Earth. And in fact, we did do it already in the early universe, right after the Big Bang. The whole universe at some point was a quark-gluon plasma, but it was extremely short-lived. And so we can get at this now from the Large Hadron Collider. This is essentially what we can measure from quantum chromodynamics. And then we can do something else where we essentially add more baryons to the system, and that changes the properties of matter. And so there's other things that we can connect to. For instance, at very large densities, it's also described by quantum chromodynamics, and you can think about neutron stars or neutron star mergers. So the thing that I want to discuss here is actually reaching this weird state of matter where it's so hot that quarks and gluons are deconfined. They're no longer stuck within hadrons. And that's right here. This is a regime where you have the exact same number of baryons to antibaryons. Okay? So to see how that looked like in the early universe, it happened 10 to the minus 6 seconds after the Big Bang. Here's the Big Bang here. We had inflation, and then we are right around here. You see where these quarks and gluons are? This is around 10 to the minus 6 seconds, and you can see here we can reach this at the Large Hadron Collider and the Relativistic Heavy Ion Collider. Afterwards, they eventually formed into hadrons, then they formed into nuclei, and then eventually to atoms, and so forth, as the universe expanded. So the question is, could we just measure this? Can't we just look at cosmology and work backwards in time to see this phase of matter for the quark-gluon plasma? Well, it turns out no. So as far back as we can reach today in time, we can look at the cosmic microwave background effect. And if we look at this, this is basically just temperature fluctuations of the universe. And so if we want to see how far backwards in time that existed, that was around 10 to the 5 years after the Big Bang. So that's hundreds of thousands of years after the Big Bang. But I want to look at scales around 10 to the minus 6 seconds after the Big Bang. So this is way, 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 way farther back in time. I cannot access that information at all from cosmology today. I need to use other methods to actually understand the quark-gluon plasma. And so this is where I want to take gold and turn it into the most perfect liquid. Is essentially what I do is I take 2 gold nuclei, I take the gold, I remove all the electrons, I just have those like chunk of nuclei from gold itself, and then I take it here, and I wrap it around this ring here. This is the Relativistic Heavy Ion Collider. This is at Brookhaven National Lab on Long Island. So you go to New York and you just travel east, and it's out there. They do tours if you're ever out there. It's pretty cool to see. And you basically accelerate these gold nuclei around the ring and smash them together at the speed of light. Well, it's okay. It's 99.9999% the speed of light, but it's pretty close. The gold were supposed to smash into each other, but my animation clearly did not work very well, unfortunately. Anyways, you'll see other animations that work a little bit better. All right, so I want to give an example. What I showed you there is a collider, but we also do things called fixed target experiments. And so that's something where you could have a gold foil, and then you shoot nuclei into this gold foil, and you see it explode. You create the quark gluon plasma in these fixed target experiments. And so back in the time of COVID, we recreated something similar as we had a water balloon right here, and then we shot a ping pong ball through this very long tube to see it explode. So it gives you an idea of what happens in the collider. Now, obviously, what we do is we have this gold ion, and they collide with each other. But let's, just pretend this is what we're doing. All right, so here's going to be the ping pong ball hitting the water balloon. You see this nice explosion of all the water coming out. That's pretty exciting. And you can see above is really cool. It just splashes everywhere. That's very similar to what we're seeing in the experiment, is we get all these particles that come splashing out. And we want to track those particles and understand their properties. And so this is an exact replica. This is what happens in the experiment, is you get these things called event displays. So this is essentially showing you where those particles splashed out when you had one collision of these nuclei. And in fact, ATLAS is an experiment that is worked on here at University of Illinois. I'm a theorist, so I'm not part of the experiment. But we have people here at Illinois who are building pieces of the experiment and doing upgrades and doing the analysis and doing measurements of this. So it's really exciting. It's something that's homegrown here in Illinois. And you end up, essentially this is where the collision is, and these are the particles flying out at nearly the speed of light from the collision. And those particles, we measure those particles, and then we analyze them and figure out what in the world happened in those collisions. So this is an example of the second, immediately after the collision, what happens to those nuclei. So they've collided, and now they're expanding outwards along the beam. And you can see that it's expanding here. It's basically moving at the speed of light, spreading out, and it's also cooling over time. Now, along the beam direction, it's kind of boring looking. They all look the same. So all the interesting physics is essentially happening in this transverse plane around the beam. So I'm going to show you another video of that going on. And this is all, to be clear, described by fluid dynamics. This is a simulation of a fluid that then we compare to what happened to all these particles shooting out of the Large Hadron Collider. And so this is a simulation of, I've taken that thing expanding, I'm just taking a slice and looking at that transverse plane. So you can see what happens there. Is it starts off very, very hot, and it's cooling, and it's going to expand in time. And so you can see that started spreading out. That is because of fluid dynamics. It's due to these pressure gradients pushing it outwards. And so you can see expanded. It almost looks like it breathes a little bit for a second. That's as it's going from confinement, or deconfinement to confinement. And this is the final state that we see at the very end. And so let's go back to this idea of fluid dynamics. And if we have a good fluid or a bad fluid. A good fluid, the kind I like, looks like this. It's water, it's flowing really nicely, it's splashing around. And then we could think of a bad fluid if we have tar. It's very sticky and viscous, and it takes a very long time to flow. And so we want something that's close to an ideal fluid. And so we can actually do this. We can look and compare our simulations to the data and extract how good of a fluid that we have. And so there's this thing called viscosity. Basically, you're thinking of this as you have lots of different layers, and it's the amount of friction as those layers rub against each other. This is viscosity, sheer viscosity. And so we can measure that, and then we can compare to things that we know in nature. And so we think about water or helium. These are generally things that we think of very good fluids. But if we then compare to what we get from the quark gluon plasma for the viscosity, it's many times smaller than these other liquids that we know and love. There's other properties, too, that can happen. You can have something like diffusion. And so diffusion is when you have some particles and you want to see how they spread out through the fluid. This would be the same thing if I sprayed perfume, and it would take some time moving through the air molecules to spread out to you all before you smelled it. Here, we can look at it in terms of ink. We can drop some ink or dye into water, and you're seeing it spread out through the water. This is another way to think of out of equilibrium effects. So what are the signatures? How do I know that I've actually measured the quark-gluon plasma? I've told you we have, but you shouldn't always just trust somebody that tells you something. You want to actually check this experimentally. All right? So I'll try and go slowly here because it's a little bit complicated. But essentially, when I have nuclei moving at the speed of light, there's this thing called Lorentz contraction. They turn into these very thin pancakes because they're moving the speed of light. And so if we imagine how two pancakes or circles hit each other, they would have some sort of overlapping regime that makes an almond shape. And so this almond shape is what is our initial condition. It's the first thing that happens in the collision. The rest of the nuclei just go flying down the beam, and we ignore them from there. Now, it's a little bit more complicated. It's not this exact pretty almond shape. That is because quantum mechanics is annoying. It exists. It moves the particles around. And so you kind of get an almond shape with little bumps all over it. But anyways, you get this dominant almond shape. And then what does fluid dynamics do? It has pressure gradients. And so just like a wave, right? If you have a big wave and you know it's going to come out this way because of the pressure gradients, it's just like that. It's like a wave of the quark-gluon plasma pushing out to the sides. And so you can see here in the simulation, you have huge pressure gradients here. And this is the initial time. Over time, it spreads out here more and more. You see that now it's looking like an almond shape where those pressure gradients were. And you can see here, at the very final state, we recover that almond shape, but in a different direction. That is just fluid dynamics. It's just the pressure gradients pushing you outwards. And so we can actually measure this almond shape in the experiment. So how do we do that? Well, have you heard about harmonics on a string, right? You can like perturb a string and you get your first harmonic, second harmonic, third harmonic. You get different shapes of the string. And so you all might have taken physics classes, learned about these different harmonics. So we can think about harmonics when it comes to the shape of the quark-gluon plasma. And so we do the exact same, because we have different harmonics, but these are in 2 dimensions. And so you can get an elliptical shape, triangular shape, a square, pentagon, so forth. And these are all overlaid in the fluid. And so when we measure the fluid afterwards, we measure all these particles coming out, we can then reconstruct what is my elliptical shape, what's my triangular shape. And there's going to be a lot of variation there, but those are things that we can measure directly in the experiment. And we can then compare big computer models to the data to see if we understand what happened. We do this in other fields of physics too. It's not just me in nuclear physics. I talked about the cosmic microwave background effect. You might have heard about this, where we measure these different harmonics and we understand the Big Bang and the early universe from that. They also measure these harmonics just like this. They have many, many harmonics. And so this is the same thing over here, where we don't measure quite as many of them. We measure up to the 7th harmonic. Otherwise, it gets really hard, because these are very, very tiny things. It's hard to get enough information. But anyways, you see here, this dot, this is the experimental data for the 2nd harmonic, which is the largest. It's that almond shape. It's telling you that we have a large almond shape. And then we have a triangular shape here and a square. And we actually do have data for these, but I just didn't show it in this plot. And so the way we understand what viscosity does is we do our simulations and then change our viscosity. If we had a ton of viscosity, my fluid would not flow. And so it would just be completely round. It would look very boring. I would not get any of these harmonics. They'd all just be 0. But when I have a very tiny viscosity, I actually see that I can reproduce the data. And that's what you're seeing here. If I keep decreasing my viscosity, it would just go to 0. And so I can compare my simulations to the data and then extract what the viscosity was in the experiment. And so this is exactly, actually this is from my group, some of the predictions we made before it ran the experiment. And you can see that it works really well. We were able to predict what was going to happen in the experiment and study what happened with the shear viscosity. And so we made a prediction that there was only going to be a very, very tiny change just at the 1% level. And the experiments were able to measure this. It's pretty shocking when you think of how big these experiments, how complicated that we can even make these type of predictions. All right, so there's another signature that I want to get in briefly. This is called energy loss. And so we can think about this is if you have a fluid and you have to like walk through that fluid. It's much harder, right? Like if you're going to the beach and you're walking through the ocean, you can feel much harder than it is walking through air. This is the process of called energy loss. You're putting in more energy. You're losing energy as you're walking through some sort of dense fluid. And so we can think of this here. If I have a ball and I drop it into a tank of water, normally the pendulum will just swing back and forth through air. But if it's going through a tank of water, it just stops. This is energy loss. Is when you have something very fast moving through a fluid, it loses energy, gets bumped around by those individual molecules within the fluid, and it stops. And so this is another thing that we can check to see that we actually produce the quark gluon plasma in the laboratory. And so there's these things called jets. QCD does this crazy thing. Imagine you have two quarks, they hit each other at the speed of light. What they do is they produce these jets of particles. They're moving at insanely high speeds, and they shoot through the quark gluon plasma. And they're always back to back. This is just due to energy momentum conservation. Yes? So we're not talking about atoms here. We're talking just about nuclei. So we are essentially, we've removed all the electrons, and you have two nuclei that are colliding with each other. And you could think of them as fusing together, but it's more creating an entire new state of matter. So the Higgs mechanism isn't playing really much of a role. You need to actually get to higher energies to calculate the Higgs and calculate its properties. So this is done in like proton-proton collisions. Is you don't have all this messy quark gluon plasma part in it. No, you don't, it doesn't affect things because all the gluons are playing a big role here. Yeah. So going back to the idea of the jets, is that you have these back-to-back jets, and then imagine that they're produced at the very edge of the quark gluon plasma. So one goes out, and you can measure all the particles from the jet. And then the other, it's back-to-back jet, right? So you've created two, one here showers out, but the other one is trying to travel through the quark gluon plasma, and it gets bumped around, it gets kicked around, it gets stuck. It loses all its energy. And so this is something we can measure in the experiments. And going back to the last example, like if you just have something like a proton-proton collision, you also make jets, but those jets just fly out, and you can see all the particles, and they're essentially the same momentum. But if you have a quark gluon plasma, you expect one jet, and the other one has lost most or all of its energy. And so this is similar to like if you want to walk through a crowd of people, you know, if one person, imagine you had a twin, and they walk through, you know, empty space, and then you walk through a crowd of people, you're going to take much longer to walk the same distance. Or you might never even escape the crowd if it has something fun going on that you want to see. So this is something also measured in the experiments, and this is an event display of that happening. Is you can see that we have one jet that very clearly came out and escaped the quark gluon plasma. It was probably produced at the edge, and its partner had to go through the quark gluon plasma, and you can see that it must have lost energy. You don't see another huge jet coming out of here. And so this is the jet energy loss. You can visually see this from the tracks. And this is an example here. You could say, okay, maybe there's a little one here, so some of it might have survived, but it definitely lost a ton of energy as it went through the quark gluon plasma. And we measure this through this thing, which is essentially taking a ratio of gold-gold collisions, or lead-lead collisions, whatever you were colliding, to proton-proton collisions. And so essentially what you see from this ratio is if it's very small, that's how many more particles you're losing, because they get stuck within the quark gluon plasma. And so we see that we have a fifth of these really high momentum particles. We've lost so many of them. We've really found this energy loss from the jets, which is exciting. Now, what's going on in the future is the Large Hadron Collider has been running for a number of years, as has the Relativistic Heavy Ion Collider at RIC. They're still ongoing. There's still a lot of cool things to measure. The story's definitely not done there. But we had something very cool happen in 2017, is we had neutron star mergers in outer space. And so essentially what neutron stars are, the way I think of it, is it's a really, really giant gold nucleus. Way bigger than anything we can create on Earth. I wouldn't want to create on Earth, we'd all be dead. But It's really big. And so you have this huge, dense, old stars, and they rotate around each other, and then they collide. And they're also described by quantum chromodynamics. The little particles inside of that, that is exactly quantum chromodynamics. And so you can look for a lot of the same things we're looking for in the Large Hadron Collider. Is you can have deconfined quarks and gluons. You could have the quark-gluon plasma inside neutron-star mergers. And it's also described using fluid dynamics. And so we're really at some initial stages here. We're just starting to get data. We're still waiting on a lot of upgrades from LIGO to get even more data. But there's a really important opportunity here to bring the knowledge from Large Hadron Colliders and the relativistic heavy ion colliders and apply it to neutron-star mergers. And so this is sort of the next phase of cool stuff. And it's bringing this and then combining it all with gravity. So it's very, very cool stuff that's going on here. And I expect you'll hear more about this in the years to come. All right, well, that brings me to the summary of my talk. Thank you for sitting here for this time and coming on a very cold Saturday morning. I hope I've convinced you that quarks and gluons are super interesting. They're the fundamental building blocks of nature. We find them all over the place. They're creating your mass, and they interact by the strong force, which is very complicated but very cool to study. This quark-gluon plasma existed right after the Big Bang, but unfortunately, it disappeared very quickly. So we need to use Large Hadron Colliders in order to study its properties. Although in the future, we're really hoping to measure this from neutron-star mergers as well. And then finally, the quark-gluon plasma is the hottest, smallest, most perfect fluid we ever known in nature. So it's something that there's a lot of cool things that are coming out, and I hope there's more to come in the years in the future. Thank you. Yeah, you can actually pick many different types of nuclei. And so gold was picked, I believe, for the first time because it sounded very cool. I don't think there was a really, you want something heavy, so you need a really fat nucleus. But we have since collided lead, we've collided uranium, we've collided xenon. Now we're going to collide oxygen. So we're trying to actually go from these really fat, heavy nuclei into very small ones because it makes things even crazier when you get to the very tiny nuclei. And the thing that we can do now with these other nuclei, gold is a double magic number, so it's very, very round. It's just a sphere. But you can think of uranium that looks like a football shape. And so we're learning now how to measure the shapes of nuclei using a lot of these techniques as well. Yeah? Okay.
So this experiment shows that light does not spread like waves, and I wonder how, and it's based on dark matter.
Okay, well, so thank you for your comment. You can ask me more afterwards if you're interested, but the stuff that we're dealing with here, we've not measured any dark matter. In fact, light reactions don't really play so much a role. They happen on longer time scales than stuff that is happening for the strong force. So it's not particularly relevant for the quark-gluon plasma, but thank you. Are there other questions? Yes?
You mentioned that there's very little viscosity in the quark-gluon plasma. How does that have so much energy loss when you have the jet scooter? I was thinking intuitively it just passes with very little loss instead of low viscosity.
Yeah, that's a great question. So the thing about the viscosity that we actually consider is the ratio of the shear viscosity to the entropy density. So we can think of this as like how dense a fluid is. The denser the fluid is, actually viscosity matters less. But when it comes to energy loss, the denser the fluid you have, the more energy you lose. And so it's a little weird. It's kind of the inverse of it. So the more perfect fluid you have, the more energy you'll lose from it. But it has more to do with the density of the fluid than anything else. It's a great question. Any? Yeah. Oh, sorry, he was answering a question up there. Yes. That's a good question. So for the neutron star mergers, this is below, you don't have a black hole yet. And so you would have to have a very, very heavy mass to produce a black hole, heavier than neutron stars. So to give you an idea, neutron stars are around 1 solar mass to 2 solar masses. We think black holes are more like 5 solar masses or above. There are some mystery objects that we don't know if they're a black hole or a neutron star. And so for those things, we're still trying to figure out which one they are. Now, if you go inside a black hole, everything is beyond the event horizon. So there could be a quark gluon plasma inside of it, but we don't actually know. Yeah, you had a question? Yeah.
I just wanted to say that in time there will be a change. First in gluons are the fundamental building blocks. What I claim in the structure of life is that the dark matter is, and the young people here would consider this idea and maybe lead
Okay. All right. You can find me afterwards if you want to talk about it more. Are there any other questions before?
Okay.
All right. Thank you.
Thank you very much for joining us. And thank you all for having a great semester with all of our presentations this year.